Sorry, from negative.
Oh, it's 0.5. Well, we're out of this. That's great. So even zeros not such, we have our zero.
It's a little bit too much talking. I hope you're staying on track with the discussions. Okay.
That's the end. Now we have this.
Oh, yeah.
Then you go like this. And then. 0, 1, 2.
And then.
Sketching. You're right, so it would be one negative e, but it's a negative e. Yeah, so we want it's shifted across. Yeah. So that's a long strike, right? Because then you charge it 5.
Oh, wait, sorry.
This charge one is by a factor, and then.
The
The negative reflects it over the y axis. Zero comma.
Well, I'm done.
Over 1. Yeah.
It was you get smaller.
Wait. So,
Yeah.
We're about done? Take about 30 seconds.
What is e to the negative 1 digit level? We do the x is the x is just.
Oh, yeah, sorry.
E, so 1 over e minus 1 over 5. The x are negative. The x That's it.
Can we label our data points in terms of E?
Absolutely. 1 over. Most exact is what I make. Oh, right. No.
Okay, folks, ready or not? Let's do this. Let's start with the parent function, which could be in your head or could be on the graph, but how many points do we need from the parent function? 3. And what is the parent function?
Yeah.
Y equals e to the x. And what quadrant should I be focusing on here? 1 and 2. Does that make sense? We don't need to worry about 3 and 4 for e to the x. Okay, and the 3 points I have, the easiest one would be
0, 5.
0. Well, just the parent function, 0, 1. So we have that 1 right here. The next point we would have on the parent function would be
On the e.
1 comma e. And where is e?
Like 3, 2, and 3.
Between a little closer to 3 because he is approximately 2.7, but I'd want this to be exact. So what I'm going to do here is mark this as E. Are we good with that? If we're on a grid, that would be between 2 and 3, pretty close to 3. The other one, of course, is when x equals -1, the y value is 1 over E, which is approximately
1 in between 1/2 and 1/3.
It's about, yeah, in between 1/2 and 1/3. I like to approximate it 1/3, but I like to even more. I like to make it exact by just calling that 1 over E. And then we have our parent function that looks like this. And I just like for you to show me in gestures when I point to one of the quantities, and I'll point to this digitally so people at home can see what's going on. Is that going to work? Let me try that again. Okay, could you please show me in gestures what is this 5 gonna do to the parent function? Please show me in gestures what that 5 does. Yeah, it is a vertical stretch. Most obviously, that 0, 1 is gonna go to 0, 5, and all the other ones are stretched by a factor of 5. Would you please show me what this negative sign is gonna do? Show me in gestures what that does. Nice. Yeah, it is a reflection over that y-axis. Good. And the 0.25, what's that going to do? Show me that one. It is a, yes, horizontal stretch by a factor of 4. It's 4 because that is the reciprocal of that 0.25, the 1 over the 1/4. I think that's what you were saying. And I think that's it. Those are all the transformations. Is that right? Okay. So let's make it happen. Again, I'm just going to focus on the top quadrants, like we said. This is gonna go up to 5. Bless you. What used to be at 1 comma E is now at 1 comma. I'm sorry, it's not 1 comma, is it? What's gonna happen to this point here? It's gonna flip.
To go up.
It's gonna stretch and go up. So it goes to negative 4 comma 5E. Okay. Which is, I think, 2.71 times more than 5, but I'll just put this up here. But this is negative 4 comma 5E. Do you have that? You mark that somehow that that's a height of 5E either on the y-axis or with coordinate pair. Cool. And of course, at negative 1 comma 1 ETH goes to
4, 5 over E.
5 over E. Exactly. Are we good with that? And 5 over E, I don't know exactly where that's going to be, but it's going to be,
1.
I know it's going to be less than 5. Exactly. 4 comma 5 over E. If you want to approximate, what would a pretty good approximation be for 5 over E? 1.8? Maybe. How did you get 1.8? Okay. So 5, it's a little bit less than 2. Are we good with that? I like that, a little bit less than 2. Because 5 divided by 2.5 would be 2.5. Sorry, divided by 2 would be 2.5. But 5 divided by 2.7, I don't know. It's less than 2.5. It's about that. It doesn't really matter. If you had to calculate, it would be easy to get. So we have that, and then I'll fudge this a little bit to make it look exponential. So this could be defined as exponential, not growth, decay. Are we good with that?
You have to label the class.
What's that?
Horizontal asymptote.
Good question. Should we label the horizontal asymptotes?
It's already there.
If it asks for it, then yes. It is already there. I did a poor job. It looks like I'm going to be floating above it. So
So if we got something that said sketch the function, would you want asymptote?
I would definitely want the asymptote for any exponential function or log. But normally I would also ask for it. So I'm just gonna fudge this a little bit, like I said, to make it easier so I can see that it does look a little bit more like an asymptote there. But I hope that the general idea makes sense. Any questions? Perhaps your question is, shall we get on with the lesson? If that's your question, the answer is yes. Yes, and you're welcome. Oh, remember when we did this? Oh, that was a good day. That day's gone. Time for another good day.
It's their
Today, there's one thing for you to memorize and many things for you to understand. The first law we're going to talk about today is called the law of uninhibited growth or decay.
I have that.
What is this? This is on the left.
And this is A equals P times E to the RT. Have you already memorized that? Fantastic. So this model is called the law of uninhibited growth. This means something is growing without hindrance, and there's some sort of growth rate happening. It's not like it grows like once every year or every 2 years. It's constantly growing, just like that money does when we divide that growth rate by infinity to get that E value. So it'll often look things like this, like M is equal to, do you know how to say this? This M with a little
Sub-zero.
M sub 0, initial M, or M naught, M naught, yeah. E to the KT, you may see it like this. But it's the same thing. This would be maybe talking about mass that would be decaying, perhaps like radioactive decay. Yeah, radioactive decay would follow this. Population, would follow this kind of same model. Yeah, and what is R? What is K? That's the growth rate or the rate of decay.
K is also the same as R.
Yeah, it's just two different variables. So this and this, these are both growth slash decay rates. Yeah. So let's see how we're going to use these. I'm not going to go over everything in these because I think you already know how to do a lot of it. The size P of a certain insect population at time T in days obeys the law of uninhibited growth. Notice that model follows exactly what we've done, except it's not talking about money, it's talking about bugs. Okay, so the bugs are growing in population. So that 320, imagine what that does to the parent function.
Oh, it stretches.
It stretches it. So that 0, 1 becomes 0, 320. And then that 0.02, that is a horizontal stretch by a factor of
200s.
by a factor of
50.
what is it? A factor of 50. Right? It's 1 over that 0.02. All right. Multiply top and bottom by 100, and you get 100 over 2. So horizontal stretch by a factor of 50. So it's growing. So like that first question, determine the number of insects at t equals 0. You see that you can either plug in a 0 or just think conceptually of, oh, we know what this graph looks like. And no, we know that it starts at 320. And if you do it that way, that is fine. But if you want to justify it, we would say that P of 0 is equal to 320 e to the 0, which is 320. What's the growth rate of the insect population? You can either say 0.02 or 2%. Do you mind if we skip C? Because all you would do is take that 10 and plug it in. I know you could use your calculators, but I do want you to do D, please. I will call on someone to help us out with that. Check with your neighbor when you get your answer. What should you round to? How many decimal places? Always 3 unless otherwise stated. Check with the neighbor once you get an answer. For D, we're skipping C.
I think.
10 seconds before I call on someone. Some lucky young student who has the name of a musical instrument. Lyra, can you help us with D, please?
So first, you said 800 equal to 320 e to the 0.02 power.
Just a minute, something is going wacky with my stuff
Can
here.
I borrow one of the calculators that are here?
Here you go. Borrow this one. So you said 800 equals 3. Oh, yeah. 320 e to the 0.02 t, you said? Okay.
Then you divide by 2.
Okay.
And then you take the natural log of both sides.
Okay. And ultimately you got that t is approximately 27, 47? Okay. 47 point
0.9.
0.
I got 45.
controversy.
Well, it depends, I guess, on what you round.
Yeah, it depends on what you round.
If you don't round, it's like,
It's 45?
if you don't want.
Uh-oh.
They want
You use the values in the economy.
So what do you think, Lyra?
That, because Byron and I, we had the same process, but that's what we got, so majority consent.
Yeah, okay. It's not always. It's not always. Yeah, but do be careful about rounding early. So 45.815.
They want that.
It's great.
Of course, I hope that you simplify this, right? At least 80 over 32, but I think 4 goes into both of these. It works out to be 2.5. Do you have to take ln to both sides? I think that's a good way to do it, but do you have to take ln to both sides?
I mean, if you multiply by,
You
you divide by.
You can take ln to both sides, or since it's exponential, you can just rewrite it as a log. Log base, log e. You get an exact thing. Log base e of 2.5 equals 0.02t. Okay, any questions?
320 into 640 just cancel out. It's just 2.
Okay, for E, when will the insect population double? We'll do the same thing. Instead of 800, it would be 640. Or would you be comfortable going to 2 equals E to the,
Yeah.
and is that something you would feel comfortable doing? You could if you want to. It doesn't matter what you start with, just as long as the second is doubled. And then you just go from there. I believe it's going to be something less than 45. That's just off the top of my head. Okay, what do we get there?
34.657.
4.657. Because that's what happens in the AP exam. They just expect 3 decimal places. So unless otherwise specified, please do that. Any questions? Perhaps your question is, can we try another? In which case the answer is yes. Strontium 90. It's a radioactive material that decays according to this function. Do you recognize that form of that function? The law of uninhibited decay in this case. Did you have a question? Okay, so A naught is the initial amount present. We knew that. And A is the amount present at time t in years. Assume that a scientist has a sample of 700 grams of strontium 90. What is the decay rate of strontium 90? Is that a difficult question to answer? There's only one common error that someone may say. The decay rate should be 0.087 or 8.7%. So a common error would be to include the negative. I hope it makes sense that you would not include that because it's already asked for decay rate. If you say decay is negative, that actually means it's positive. So be careful. Is this all new? Like, take a look at it. Is this going to be difficult to do? Do you mind if we go on to the next problem?
Wait, half-life.
Yeah, half-life, just instead of 2 equals, your 1/2 equals.
Yeah.
And here it tells us that we start with 700, but you could just write like 1/2 the initial amount equals A naught e to the 8.087t. Either way, we get to 1/2 equals instead of 2 equals. Thank you for pointing that out. That is a significant difference. And then the A naughts cancel. Or the 700 and the 350 to 350s cancel. This one, a culture of bacteria obeys the law of uninhibited growth. They didn't tell us a formula here. Could you write a formula for the population of the bacteria? Please use K for the growth rate for A. Please check with your neighbor. Once you are done or stuck, I want to call on someone to give us an equation, just an equation for this. No numbers involved, just quantities.
And the starting amount.
Good question. Do you have something?
He says you can, but not well. So,
Ooh, these are.
exactly, R is such a weird, but.
It's a pirate letter. Okay. I want to hear from Justin. What'd you do for A?
I said function NFT equals M naught E K K T.
EKKT.
No,
Oh, no.
no. E to the K T.
Oh, E to the KT. Are we good with this? Thank you. That's exactly what I was looking for. I like how you said that the N of T. Thank you. It's not essential, but that's really nice that you included that. I'm going to keep it like that. It would be okay if you didn't put that there. If you just put N is equal to N not E to the KT, it's fine too, either way. But it says express N as a function of T, so that's very specific there. So if 600 bacteria are present initially and there are 800 after 1 hour, how many would be present in the culture after 5 hours? Let's get a picture of what's going on here. This thing started at 600. Then after 1 hour, it grew to 800. And the question is asking how many will there be after 5 hours? So I'll give you a minute to find a strategy. And I'm going to ask you what you did.
No, we already know.
No decimal points.
We need to know the rate.
The amount. Here's the.
But you just use your little.
Sure.
But then the rate is 130 because it's getting growth by 33. I got 0.7.
That's all.
608. I got 0.28. But you have to keep this number under, right? So use your growth rate. 600. Natural log. 0.67%.
Yeah.
Okay. I would take this.
I say
Oh, this is wrong.
Because I'm doing this simple. Well, then I don't.
Curious.
First,
And then do E to that.
That's a lot of bacteria.
Yeah, because it's not like you have to run down.
I got 2,528.
Did you get something?
No, this is probably two. Just hang on. Yeah.
how many?
Yeah, it is for sure.
Plus K.
I don't know.
No, you didn't.
Yeah, it's just N of 5. I was saying, okay.
Did you do it? Yeah, I can.
Why is it one?
Oh, so yeah, so
It's pretty good.
just say some words with.
Yeah, sure. No, I assume you don't have to round for like a
Oh,
question.
yeah, but it's zero.
I love the unround. I got like 2,528.
Yeah, that's it.
Oh, yeah, it's 3.5.
Are ready? Okay, I need to hear some sort of strategy. What do we do with this? Maya, what do we do?
Okay. By plugging all the numbers in, so like.
Okay, before you move on, are we okay with that? Solving for K first? Remember, K is the growth rate. So we have to know how fast is this growing. Okay, so go ahead, Maya.
I did 800, so it was 600 bags. And then when I like solved for K, I got 0.2.
Okay, approximately 0.288. Is that appropriate to round to 3 decimal places here? Is it okay? I said 3 decimal places. Is it okay to round to 3?
This is not.
At the end round to 3. This is kind of a midway point. So since you're using a calculator, please use everything. Are you all okay grabbing a number and using it? Just go to that number and hit enter. Make sure you're not retyping. I'm happy to help with that another time. Okay, so Maya, so we're going to take that value that you got, and then what?
The K that we found and then times 5. But the 5 is still a 50 dash.
Okay, so you have 600 times e to the 0.288. I'm going to put dot, dot, dot in there. And then the 5. And what did you get?
1,528.395.
28.395. Do we agree with the number? And the initial, but before we put more thought into it, are we okay with that calculator coming up with that number? Hey, Maya, did you have anything else to say about this one, or what's the units here? Bacteria, right? We're counting bacteria.
I think a fraction of bacteria.
Do we agree that that's a valid question? So what should our answer be?
Round it.
Should we round it?
I'm down.
Round down.
Like if we have 0.8 bacteria, does that count as a bacteria? If we have 0.99 bacteria, does that count as a bacteria? That's so sad. Yeah, what is it? Kind of, right? Maybe it's just growing. I don't know. I'd say round down and say you can't have a portion of a bacteria, right? Give me a little statement. So here,
We get range just like 1 bacteria.
yeah, I'm more interested in the thought process and then seeing what you do at the end. Definitely don't round that K value until the very end.
We get points up on the chance to be right. There's 0.395 bacteria.
Quite possibly.
You were more concerned with the thought process.
I am. Well, it's not binary. It's not binary. It's not all or nothing. It's like if there are 8 points, so you get 7 points for all the calculations and 1 point for not having a portion of a bacteria kind of thing. And that is thought. And it's a process. But I want to show you something else here. And Maya, thank you for your help with this. I'm going to take us back here. And the next step, of course, from there is to divide by 600, isn't it? Where we get 4/3 equals e to the k. Do we agree with that would be next step? And yeah, how about we just take that e to the k and plug in 4/3? What do you think? That's fine. We could make n of t equal to our initial amount, which we know is 600, times 4/3 to the t, which is nice and simple and no rounding. Could you check your calculator what happens if you plug that in? And it would be an 8, of course, that you plug in. Not an 8, a 5 that you plug in. Excuse me. Isn't it's pretty nice. The question never asked you to solve for k, so we solve for e to the k and then use that. Just something you could use to help your calculations along. It's faster and more accurate. So how long is it there until there are 20,000 bacteria? Is that a difficult thing to solve? Same thing as we've had. Okay. Last order of business. Newton's law of cooling. Have you spoken about this in any of your other classes? No, not in your Spanish class. They didn't talk about Newton's law de cooling. Just kidding. Okay, well, I do have a question for you. Will you please put up your hand if you've ever baked cookies? Okay, and not a single person has brought me one. Okay, you've all baked cookies and I've received none. See how it is. That's fine. I eat them immediately too. Um, so let's say, what's a good temperature for baking cookies? I don't even know. It's been so long.
350.
350 Celsius, 350 Celsius.
Oh.
50 Celsius. They just catch on fire immediately, I believe.
50 though?
350 at 350 Celsius. Like, so 350 maybe. So let's make a graph. Let's make a, for instance here, let's focus on the first quadrant. So let's say you take the cookies out of the oven at 350 and we're graphing the temperature. So it starts at 350. Now, if the cookie didn't cool, then your graph would just look like
No.
this. Because this is a t-axis. But we know that eventually you are able to eat the cookie because it cools down. What I'd like you to do is make an approximate graph for what you think the temperature of the cookie takes. What do you think? What would it look like?
It's a.
Yeah, so you for all the choices.
Oh my God, you think that's out of class? Oh my God, that's how it works. Were you sad there? I don't understand that.
Has to reach thermal.
Yeah.
temperatures.
Okay.
Because it's like.
So folks, on the whiteboard in front of you, take your finger marker and will you please just kind of trace the graph that you made on your paper? So I'm seeing this, is that right? No? So kind of like this.
Oh.
Oh, that'd be ridiculous. Oh, yeah, so I think this is what you showed me. So something like this? Are we good with that?
When it comes to the volume.
When it's
Going to like room temperature.
That would be a very,
Very,
very cold kitchen. And so more likely the temperature will decrease and it decreases fairly quickly. Doesn't it immediately decreases quickly? But it doesn't decrease to zero. It's going to decrease to
temperature.
the temperature of, yeah, until you eat it. Let's say you don't eat it though.
Oh my God, the temperature of the room.
The temperature of the room, which let's say it's 70 degrees.
Again, pretty small.
70 degrees. So that 70 becomes a horizontal asymptote. So do you think it's actually ever going to hit that 70 degrees? In Sage's house, it will stop existing at this moment. Is this correct? Yeah, in my house, it exists here, and I'll just deal with the blisters. Yeah, I can't wait. Can't wait. But I'm sorry, do you think it'll hit that 70 if it's not eaten?
It could, it would be like
It'll
down.
be like.
Kidding.
It'll probably hit it. But theoretically, what Newton said is that something that's taken out of its environment and then left to cool cools at a rate that is exponential, right? This is exponential, specifically exponential decay. That's Newton's law of cooling. And it also applies to heating. Imagine you took something out of the freezer. It's not going to stay frozen. It's going to exponentially heat. But
That's it, linear.
great question. Why isn't it linear? It's based on his observations. And I think also our intuition, if it's linear, is it just going to crash and then just stop? I think we know just from experience that it cooled off pretty quickly in the beginning.
As it gets colder, it's not gonna keep getting colder at that same rate. It's gonna
Yeah.
like slowly get less cold.
Oh, nicely said. As it gets colder.
It won't cool down at the same rate.
Yeah, that difference won't be as extreme, so it'll kind of slow down and cooling. That's nicely said. And you can imagine if it were even hotter, it would start off like really strong decrease. And Newton studied this. And he found that this is true. So let's make an equation, shall we? Let's make an equation for this situation. But let's generalize it. Let's say that this is A for ambient temperature.
Really?
Do you want to use something else?
What?
Or R? Maybe R for room temperature?
A.
Ambient? Yeah.
A for.
A for, yeah. Yeah.
Say it.
No. We'll say that this point here is little t, comma, big T.
They're missing the same steps.
What? Let's say that just a point on the graph is little t, so however much time has passed, that's the temperature.
Oh, yeah.
So big T is a variable, little t is a variable. So what should we call this right here?
Zero.
T naught.
T naught, shouldn't it? T naught right there.
Zero.
That is T naught. Do the cookies in the oven actually get to 350 degrees?
No.
Because that's also like Newton's law of heating. It's going to get close to 350. But anyway, well, imagine they come out at 350. Or something's going to have an initial temperature and then it's going to start the ambient temperature. I can give you a minute to see if you could figure out this equation. I think you can.
No, I think it does. Well, because heating law means this.
Yeah.
Is heating law presumably just the input?
No, it's-
38.
Plus.
Yeah.
There's your A.
Plus.
Plus.
T naught
Yeah.
minus.
Oh, it's just.
Okay. I'm keeping this as a thought bubble just so because we have that exponential function to reference. A is a little confusing because in this one, A represents amount, as opposed to this, which is different. So ambient temperature. So let's think, what is P gonna be?
Jason.
We have variables. No, I've taken all the numbers.
T.
T.
Whatever the zero.
Are we good with P equaling T naught?
Yeah,
It's not.
it's not.
It's not.
Is it?
Oh, it's not.
Is it?
Is it? Oh, wait, no, is it not minus A?
Minus A. And normally that stretch, without the stretch, it'd be just one. Right? It would just be one right here, but this is stretched. And this,
And you have to add A.
yes, we have to add A, right? This is a vertical shift. So this is our stretch right here. So that's what our P is equal to. So let's see, this is T naught minus A. Let me put this together. This is T naught minus A. R, we'll keep it as R T. And A is no longer A, it is now T. And what else do I have to do?
Plus it.
Plus A. A. So this is Newton's law of cooling. I'm not going to ask you to memorize that formula. But I'm going to ask you how to, yeah, I'll be giving it to you. And so you're just going to have to be able to use it. I'd like to do some practice with this, but I'm afraid it's going to have to wait until next time because it's just about time for quiz. So right now, if you need to stretch, you can take a couple minutes to do that. If you need to zone out for a couple minutes before the quiz is on the hub. So just whenever you want to start, I do want a sheet of paper turned in.
Oh.
I do want you to turn in your work. I do want you to turn in your work. Remember it, please. And you don't need to calculate. No calculator.
What if there's a lot of mental math done?
That's fine. But if it's not mental math.